After studying this module, you shall be able to know what are SALC, symmetry adapted linear combination. Learn how we can get these SALC. Learn the basis for SALC formation. Learn how to use bond vectors for the formation of SALC. Learn the use of projection operator for generating SALC for particular symmetry spaces. Find SALC for water molecules using 2H bond vectors as the basis. SALC, symmetry adapted linear combination of atomic orbit. Now, in earlier modules on symmetry properties of the molecule and group properties, we have learned how to classify the molecules into various point groups, how to get reducible representation using various basis function. We have also come across a method of reduction of reducible representation to irreducible representation through great orthogonality theorem. You have learned about the relationship between reducible representation and irreducible representation. What is character table? How it can be constructed also was learned in earlier module. In this module, we will learn the application of symmetry, molecular symmetry and group theory in finding symmetry adapted linear combination of atomic orbital. Symmetry adapted linear combination of atomic orbitals. What we mean by this? We have taken bond vectors as the basis for representation. Bond vectors or the bonds involved in the overlapping of atomic orbitals as the basis for reducible representation is very important in finding the symmetries of the orbitals or atomic orbitals involved in the bonding. These type of informations are very important in dealing with the problems of chemical bonding, molecular orbital formation, hybrid orbital formation, ligand vein theory and vibrational spectra of the molecule. In this module, I will discuss what are SALC, how these can be formed. Now, let us discuss SALC by taking few examples. For example, the case of xenon tetrafluoride, we can use 4 xenon fluoride bond vectors as the basis for representation and get tau reducible or tau xenon fluoride as given in this table over here. That is, if we take the 4 bond vectors and see the effect of symmetry operation on these 4 vectors, and we have already seen if the bond vector is shifted, it contributes chi to the reducible representation. If bond vector is unshifted, it contributes +1 to reducible representation. If bond vector is unshifted but only direction is reversed, it contributes -1 to the reducible character. Taking these into account, we get the characters for tau xenon fluoride or tau reducible as for E it is 4, then C4 0, C2 is 0, C2 dash is 2, like this C2 double dash 0, I is 0, and then we have 0, 4, sigma H is 4, sigma V is 2, sigma D is 0. So, like this, by making xenon tetrafluoride and 4 xenon fluoride bond as the basis, we get the reducible representation as this. Now, following the standard method of reduction, this reducible representation can be reduced to A1G plus B1G plus EU. What it means to us? Here 4 base vector, that is the 4 xenon fluoride bond vectors, can be used to form 4 linear combination, either their sum or their differences, or there are some oblique differences such that one of such combination transforms or belongs to symmetry as A1, another transforms as B1G, and the remaining two combination transform as EU. Similar results can be obtained in for n functions of a function space as the basis for representation. For example, 3p orbitals, 5d orbitals can be used as functions for finding tau p or tau d. From these results, it is possible to find n symmetry adapted linear combination, that is SALC, corresponding to specific irreducible representation. For finding symmetry adapted linear combination for simple molecule, we can just do it by inspection method. That is, you can just see and you can predict what type of basis SALC will be there. We know that LCO means, and just by inspection we can tell in few cases what are the LCO is of lower energy, what is LCO of higher energy. But this is not a general method and cannot be applied always. Here we will discuss a general method of getting SALC. This is called projection operator method. What are projection operator and their theory will not be discussed in this module. The use of projection operators in projecting out the desired symmetry adapted linear combination of atomic orbitals which will correspond to desired irreducible representation, that is, which correspond to desired symmetry. General form of the projection operator. Now, I will just tell you what is the projection operator which operates on function space and that generates SALC of desired symmetry. Now, for this I will take a equation which we call as the projection operator equation. Now, let us take the general form of the projection operator which can operate on a function space and generate the desired function of desired symmetry. The equation given over here is the projection operator, where the various symbols have the definite meanings. Tau I p, that is a operator corresponding to irreducible representation tau I, operates on function fj is equal to ni upon h, that is, this is a constant also. Chi ir, that is the character of irreducible representation of ith irreducible representation. Chi I is the character for tau I irreducible representation. Or fj represents the transformation operator operating on the function fj. Then what is the next? Net result is there. So, in this we are having three basic things, that is, we take the projection operator corresponding to the desired irreducible representation. We require the characters of the desired irreducible representation, and also we need transformation operator corresponding to R which acts on the function space. And here the where ni upon h is the constant factor, ni is the dimension of the ith irreducible representation of the point group, h is the order of the point group. Constant is usually irrelevant. The constant before wave function is generally determined by the normalization condition specific to the problem under condition. So, this basic equation of projection operator is very important. So, in order to apply this projection operator, we basically know the effect of OR on the function space. We also know the chi I R, that is the character for irreducible representation, and we also know for which irreducible representation we are going to apply the projection operator. This projection operator sums over all the symmetry operation R the product of character of ith irreducible representation chi r, chi ir, and the effect of OR on function space Fj. That is, the sum is taken over all operation R of the terms chi ir into OR into Fg. So, that is, the product is of mainly 2. Again, class cannot be grouped together. For example, in C3V point group, 2C3 operation in a class represents C31 and C32. Here it is very important. We have to take the effect of OR separately for C31 and C2 symmetry operation, and R to be considered separately. 3C2 operation in D3H point group have to be considered separately, and these have different effects on functions. Projection operator is also known as the function generating machine, because just by applying the projection operator on a function space, it immediately projects out the desired function which belong to the desired molecule. It automatically projects out the correct linear combination for the formation of symmetry adapted linear combination, and this SALC will be of desired right symmetry. Now, let us try to take the bond vectors as the basis for the formation of SALC. And let us take the simple example of water molecule which has only 2 OH bonds, which are represented as R1 and R2. We take these bond vectors as 2 functions, and these are shown in the figure below, that is OH bond as R1 and R2. Besides this, various symmetry operation in these molecules or symmetry elements in these molecules are shown together with sigma yz, sigma xz and C2 x's. Now, we will make use of this R1 and R2 to generate the desired SALC. By inspection, we can work out 2 SALC for 2 bonds as R1 plus R2, that is the constructive overlap, or R1 minus R2, that is the destructive overlap. But we are interested into the general method. We always do not deal with simple molecules. So, there must be a scheme, there must be a method which is used for general. Now, the various steps involved in a general methods are as follows. First, the point group of the molecule must be known. Here in this case, it is C2B point group. Then we must attach bond vectors to each and every bonds. Here we are using R1 and R2 as bond vectors, that is, each is attached to OH bond. Then, making use of these R1 and R2 bond vectors, find reducible representation. That is, I have to see the effect of E operation, C2 operation, sigma xz operation, sigma yz operation on R1 and R2. These effects of various operations belonging to C2B point group are summarized below over here, and we find over here either I say E or I can say OE, that is transformation operator corresponding to E, sigma V or corresponding to sigma, that is operator corresponding to sigma yz or sigma xz, and all these effects are shown over here. And by making use of these effects and making use of the fact that the vectors which are shifted do not contribute to the overall character of reducible representation, vectors which are unshifted contribute character is equal to +1 to reducible representation, vectors which are unshifted but only direction is changed contribute -1 to the overall character. So, by taking this into account, let us try to find out the reducible representation by making use of the bond vectors. Two OH bond vector stretches R1 and R2, C2 axis lies into YZ plane, XZ lies perpendicular to the YZ plane, bisect HOH angle. Character table, partial character table for C2V point group and effect of transformation operator corresponding to E, C2, sigma V and sigma Z is shown over here. That is, last 3 rows they give R1, R1, R2, R2 like this, what are the effect of this symmetry operation. Now, once we get the tau reducible as 2002, that is, we take the effect on R1, we take the effect on R2 and then we take the overall effect on R1 plus R2, and the tau reducible is 2002. Now, this tau reducible 2002 can be reduced to irreducible representation by following standard reduction formula. Therefore, tau reducible over here is A1 plus B2. Step 4. Let us now use projection operator corresponding to A1 plus A2, B1 plus B2, irreducible representation of C2V point group, and find the SALC. Let us take A1 irreducible representation and use the corresponding projection operator on function R1. That is, R1 here is Fj. The projection operator is A1 P operating on R1, Ni upon H summation R character A1 into R, OR operating on R1, H is equal to 4 and Ni is equal to 1. By making use of this, we get is equal to 1 by 4 chi A1 E into OR OE on R1 plus chi A1 C2 OC2 on R1 chi A1 sigma XZ O sigma YZ on R1 chi A1 sigma YZ O sigma YZ on R1. So, we take this and now let us write down this result. It is 1 by 4 1 into R1 plus 1 into R2 plus 1 into R2 plus 1 into R1 is equal to 1 by 4 2 R1 plus 2 R2 2 by 4 R1 R2. That is, here R1 and R2 here 1 2 is ignored because we have to normalize this linear combination later on. Let us now take A2 irreducible representation and use the corresponding transformation operator A2P operating on R1, Ni upon H summation R chi A2 operating on R, OR operating on R1, H is equal to 4 and Ni is equal to 1. Again we write down similar equation 1 by 4 within bracket chi A2 E O E operating on R1 chi A2 C2 O C2 operating on R1 chi A2 sigma XZ O sigma YZ operating on R1 chi A2 sigma YZ O sigma YZ operating on R1, and we have the result as 1 by 4 1 into R1 plus 1 into R2 minus 1 into R2 minus 1 into R1 0. That is, no linear combination of R1 and R2 belongs to this A2 irreducible representation. Now let us take B1 irreducible representation and follow the similar procedure. Now let us take transformation operator corresponding to B1 and follow the procedure as described. That is, B1 P operating on R1 Ni upon H summation R chi I R, that is, we are taking the R1, then OR operating on R1 H is equal to 4 Ni is equal to 1. That is 1 by 4 chi B1 E, OE operating on R1, chi B1 C2, OC2 operating on R1, chi B1 O sigma XZ operating on R1, chi B1 sigma YZ, O sigma YZ operating R1, and we have the result as 1 by 4 1 into R1 minus R2 plus R2 minus R1 is equal to 0. No linear combination of R1 and R2 belongs to this B1 irreducible representation. Let us take B2 irreducible representation and follow similar procedure. B2 P R1 Ni upon H chi R chi B2 R OR operating on R1 H is equal to 4 Ni is equal to 1 is equal to 1 by 4 chi B2 E OE operating on R1 plus chi B2 C2 OC2 operating on R1 chi B2 sigma XZ O sigma XZ operating on R1 chi B2 sigma YZ O sigma YZ operating on R1. 1 by 4 is equal to 1 by 4 1 into R1 minus 1 into R2 minus 1 into R2 plus 1 into R1, that is 2 by 4 R1 minus R2, or is equal to R1 minus R2. That is, this combination belongs to B2 symmetry. We have seen the effect of OR corresponding to A1, A2, B1 and B2 irreducible representation and observed that we get SALC corresponding to A1, B2 irreducible representation only. Applying projection operator corresponding to wrong symmetry will always give 0 as the result. This means wrong transformation projection operator will annihilate all the function and accept the desired function. The linear combination, that is R1 plus R2 and R1 minus R2 corresponding to A1 and B2 symmetry, that is to symmetric and anti-symmetric stretch OH bond respectively. Figure 3 gives the symmetric and anti-symmetric. A1 means both the OH bonds, they stretch simultaneously in one direction. Either they go away from the oxygen or they come towards the oxygen. These are of A1 mode. In B2 mode, one of the OH bond stretches and another OH band is moves towards oxygen. Another goes from oxygen away from oxygen. Like this, two bond stretchings are A1 on of B2 symmetry. These are the results obtained by taking R1 function. Now let us take R2 function and see the effects of transformation operators corresponding to particular irreducible representation, and these results are listed as A1 P operated on R2 Ni upon H summation I chi A1 operated on R OR operated on R2 H is equal to 4 Ni is equal to 1, and the result for R2 is 1 by 4 chi A1 E OE operated on R2 chi A1 C2 OC2 operated on R2 chi A1 sigma XZ O sigma xz operated on R2, chi A1 sigma yz, O sigma yz operated on I2, and the result is 1 upon 4 1 into R2 plus 1 into R1 plus 1 into R1 plus 1 into R2. That is, the net result is 1 by 4 2R1 plus 2R2, or 2 by 4 R1 and plus R2, or R1 plus R2. Now, let us apply projection operator corresponding to B2, that is B2P operated on R2, Ni upon H, summation R, chi B2 corresponding to R, OR operated on R2, H is equal to 4, Ni is equal to 1, and the net result is 1 by 4 chi B2E OE operated on R, chi B2C2 OC2 operated on R2, chi B2 sigma xz O sigma xz operated on R2, chi B2 sigma yz O sigma yz operated on R2, and we get the result as 1 upon 4 1 into R2 minus 1 into R1 minus 1 into R1 plus 1 into R2, that is 1 by 4 2 R1 minus 2 R2, 2 by 4 is equal to R1 minus R2, or equivalent to R minus 1 R2. Similar results are obtained earlier. Let us take the projection operator corresponding to A2, which is operated on R2 function, and the results are 1 by 4 R2 plus R1 minus R2 0. Similarly, let us operate projection operator corresponding to B1 on R2. We will get the result 0. By using R1 and R2 as the base function and using all irreducible representation of C to B point group, we got only two SALC as R1 plus R2 and R1 minus R2. To normalize these two SALC for H2O bond vectors, these must be multiplied by a factor of 1 by 2 under root, that is, normalizing linear combinations are 1 upon 2 R1 plus R2, 1 by upon under root 2 R1 minus R2. The required normalized constant for SALC is 1 upon under root n, where n is the sum of square of the coefficients of individual function in linear combination. The required normalized constant for any SALC is 1 upon under root n, where n is the sum of the squares of the coefficients of individual function as linear combination. Let us check whether results that we have obtained so far are true or not. Each linear combination has the right symmetry or not, that is, each combination belongs to desired irreducible representation or not. The linear combination R1 plus R2, which belongs to A1 symmetry, is left unchanged by all symmetry operation of C to B point group. To check this, we put the effect of OR on R1 and R2 in linear combination of R1 plus R2 and R1 and minus R2. The results are summarized over here. That is, we take A1 and we take the OR R1. The result is this. We take OR R2, the result is this. Therefore, effect of A1 on R1 plus R2 is the same, it is not changed. And here also we see in the case of R1 and R2 remains unchanged under symmetry. Now, similarly, we can make use of the R1 and R minus R2 and see the effect of B2 symmetry. R1 and R minus R2 remains unchanged under B2 symmetry. This R1 plus R2 combination remains unchanged under A1 symmetry, and R1 minus R2 combination remains unchanged under B2 symmetry. Here we have taken all the four reducible representation A1 and A2, B1, B2 of C to B point group. we should have taken only those irreducible representation for which R1 and R2 bond vectors form the basis. We have seen earlier that reducible representation obtained by taking R1 and R2 bond vectors as basis on reduction gave irreducible representation as A1 and B2 only, and there is no A2, B1 in it. So, we should find SALC corresponding to A1 and B2 irreducible representation only. This reduces our task to a greater extent. That is, only we have to take projection operator corresponding to only those irreducible representation which are obtained from reducible representation. So, in the end we can say what we have learned in this model. We have seen what we mean by symmetry adapted linear combination. It has been explained. Now, method of getting symmetry adapted linear combination is explained. Basis for SLA formation is explained. An example for finding SALC using bond vector as the basis and by taking the example of a molecule is also explained. Use of projection operators for generating SALC for particular symmetry species has been discussed in detail. SALC for water molecules using two OH bond vectors as basis have been obtained, and correctness of these SLA obtained have been checked. Now, we have also learned over here that there is no need of using projection operator for each and every irreducible representation of the point group. We should take only those irreducible representation of the point group which are obtained by reducing the reducible representation, that is a representation which has been obtained by taking bond vectors as the basis. SALC, symmetry adapted linear combination for water molecules using two OH bond vectors as basis have been obtained, and correctness of these SALC so obtained has been checked. So, what we have learned in this module, that is what is a projection operator, how I can operate on a function smith. I can say this projection operator is a function generating machine. This operates on a function and it projects out only that function which is of right symmetry and which belongs to this molecule. And this is the in nutshell that we can apply projection operator on the molecules and we can get SALC corresponding to these molecules.